Hello everyone, today I'm going to go over a question involving a separable differential equation, which was a area of discussion that I think a lot of students were struggling with, and hopefully another extra problem going over them will make it a little bit more easy, a little bit more understandable. So this question involves wolves and this function p of t. They say let p of t represent the number of wolves in a population at time t years when t is greater than or equal to 0. The population p of t is increasing at a rate directly proportional to 800 minus p of t, where the constant of proportionality is k. Now, right off the start, it's a little bit confusing the way they word this with the is directly proportional, where the constant of proportionality is k. That is a really weird way of stating just the basic differential equation that this is going to be based off of, which is that p prime of t equals k 800 minus p of t. Now, if you weren't able to just get that from this weird wording they have, I wouldn't be too worried about it. This is an older question. I haven't seen anything like this in recent tests I've taken. So the strange constant of proportionality language, I wouldn't worry about it. As long as you have this to start with, you're good to go. So, going right into the problems, A, if p of 0 equals 500, find p of t in terms of t and k. So, right off the bat, we're going to need to turn this into a separable differential equation that we can use. So, just to go ahead and simplify the notation here and make it a little bit more conducive, I'm going to change that p prime of t just to p to dp over dt. And since p is a function of t, hopefully it's implied that this is p of t, and that is going to equal k 800 minus p. Now, whenever you have one of these separable differential equations, the most important thing is you want the dp term and the dt term to be on sides of the equation where they are with whatever t's or p's are in the equation. So if that didn't make sense, hopefully I'll just go ahead and do some algebra that will hopefully make a little bit more sense. Since this term, this 800 minus p term, has a p in it, we want it to be on the side with the dp. So we'd have dp over 800 minus p, and on this side, we'll pull over the dt, we'll have k dt. Now, this is the point where the calculus comes in. Since you have the dt on this side, the dp on this side, you can just go ahead and integrate both of them. Now, the integral on the right is super easy, so I'll just go ahead and do it first. We're going to have just kt, basic integral, but don't forget, we'll have the plus c. I'm choosing to put the plus c on this side. With a differential equation, you can put it on this side or that side. It's not really important. Now, this section, you are going to have to use a little bit of u substitution. Maybe you can do this in your head at this point, but I'll go ahead and throw in u equals 800 minus p. Therefore, du equals, oh, that's a minus. Du would equal negative p dp. Oh no, just negative dp. No p there. So you can simplify this down to du over u equals that, which of course you can change to natural log of the absolute value of, and instead of putting u, I'll just go right ahead and substitute that back in, 800 minus p. And that equals kt plus c. Now, oh, whoops, looks like a little bit was out of the camera there. Now we have to do a little bit of algebra. We're going to exponentiate both sides. So you'll get 800 minus p equals e to the kt. And in this instance, I'm just going to go ahead and take the c term and make it negative because, or no, not make it negative. I'm going to pull it out of the expression because we'd have it up here, but remember, if you're adding something in the exponent, that's the same as just multiplying by it. And so we'll just take this out, and I'm going to call it C1 just because it's going to be a different value from this original C. Now, I should note This would technically be plus or minus since we're dealing with the absolute value. But remember, in this instance, we're not going to have a negative number of wolves. So it's fine just to leave this as C1. All right, brief pause there because I did realize I had a mistake in there. Hopefully you picked up on it before I did. I never factored in this negative sign up here because it wouldn't be du over u, it would be negative du over u, and this would be negative natural log of 800 minus p. And then we could have just multiplied everything by -1 on this side, and that would have ended up just having negative kt over here. So everything is kind of the same, not too much has changed, just make sure you have that negative sign there, my mistake. Now, this is the point where I'd recommend trying to find your C. It's a little ugly, we don't really need it in there, and this is when we'd pop in this initial condition, p of 0 equals 500. So for p, I'm just going to plug in 500, and for C, I'll plug in 0. E to the negative kt would just be e to the negative k0, e to the 0, 1, which means we don't have to even write it in, and C of 1 equals 300. So now with that out of the way and with a little itty bitty bit of algebra, you can find that P of t equals 800 minus 300 e to the negative kt. And oh, that is still out of it. All right, so there you go. That is your final equation in terms of t and k. Now we're going to go on to b, which just throws in another initial condition and tells you to find k. And this one is super duper simple because we're just going to take this equation we already found and plug in the numbers they gave us to find a new equation. So we have p of 2 equals 700. So we'll have 700, we're plugging that in for p of t, equals 800 minus 300 e to the negative k t, which would be 2. So negative 2k. Hopefully that's visible. From here, algebra, we'll have 100 equals 300 e to the negative 2k. Over here, we'll end up with the natural log of 1/3 equals negative 2k. And we'll have the negative natural log of 1/3, which would just be natural log of 3 over 2. And hopefully you can follow that the result is the natural log of 3 over 2. There we go, that's our k term. Still, I keep writing outside of the camera. Hopefully that was all at least understandable, even if a little bit of it ended up outside the camera. Now, lastly, I'm going to do part C, and this asks to find the limit as t approaches infinity of p of t. Luckily, we already have our equation for p of t, so at this point, all we need to do is limit as t approaches infinity of, and we're going to grab this p of t equation right here, 800 minus 300 e to the negative, and in fact, we can take our k term, our k term, which is natural log of 3 over 2, plug that in, and t. All right, from here, this 800 is just going to be a constant, so we can pull it out. We'll have 800 minus the limit as t approaches infinity of 300, and in fact, I will invert this section. Hopefully that'll make it more obvious what's about to happen. 3 over 2t. Now, as t approaches infinity, this whole section, natural log of 3 over 2t, is going to blow up to infinity. And therefore, e to the power of that is going to blow up to infinity. And what happens is you have 1 over infinity, which means this whole section is just going to approach 0. So the result is just that the limit and I'll rewrite it here, the limit as t approaches infinity of p of t equals 800. There you go. And I just want to point out really quick before I close out, that this should make a lot of sense. Now, if you look, I'm going to just draw a quick little slope field. Imagine this is p, this is t, and here we'll have 800. Now, if you take just the original differential equation we have up here, dp over dt equals k 800 minus p. Now, when t is equal to, when p is equal to, or roughly equal to 0 around this area, this is going to be roughly 800k, which means the slope is going to be really positive. I'm drawing a slope field here, if I didn't make that clear already. It's going to be super positive all the way down. Then, as you're closer to the middle, this 800 minus p term is going to look a lot more like 400, 800 minus 400, and so you'll get k times 400. So it's going to be a lot more slanted along that section. And then, as p gets really, really close to 800, you're doing 800 minus roughly 800, and so the slope is going to be basically 0 as you're closing in there. So I'll try and make that clear. So as you look at this slope field, it should become really, really obvious why the limit as t approaches infinity of p of t equals 800. Because if I start anywhere on here and I follow these slope lines, I'm going to end up with that horizontal asymptote at 800. So obviously, if you're doing this problem in person during the exam, you're going to have to do this more formal proof. But this is a really good way to check if you're able to just quickly visualize what that differential equation would look like in slope field terms. And when you do that, it should become really obvious that you have this horizontal asymptote as it's approaching infinity at 800. Anyway, that closes out the video. Hopefully this was somewhat helpful, and see you all in class, and good luck on the exam.